So if you're determining a formula, the first thing we're going to look at is percent composition. So we have our mass of the desired element over the total mass, which is really how all percents are calculated. It's always the part over the whole times 100. So percent composition is a very useful tool to determine the amount of an element in a compound. Since it is based on the total mass, the percent composition of an element in a compound is independent of the amount of that compound. Right? It's a percent. So if I was to ask for the percent of nitrogen in ammonium sulfate, the first step is to get the molar mass for the entire compound. Nobody expects you to ever show your work for how you got the molar mass of the compound. You should be able to do all of this in your calculator. Just looking at the formula, you go, okay, 2 times the mass of nitrogen, plus 8 times the mass of hydrogen, plus 1 times the mass of sulfur, plus 4 times the mass of oxygen. Plug that all in one stream in your calculator, hit enter. That should be your molar mass. You might want to look back and make sure you've counted the right number of each atom, but besides that, your molar mass should always be fine. So to find percent composition, it's the whole part over the whole. So my part of nitrogen is 28.2 over the whole, which is 132.17. I end up with 21.20%. All right, so if the problem asked for the number of grams of nitrogen in 402 grams of ammonium sulfate, we can solve this in 2 ways. The first way is going to be just basic dimensional analysis. You don't have to do anything with percent composition. I start with 402 grams of the total. There is this many grams in 1 mole of ammonium sulfate. For every 1 mole of ammonium sulfate, there are 2 moles of nitrogen. Then for every 1 mole of nitrogen, it's 14.01 grams. Multiply the top, divide by the bottom, and that gives me my grams, 85.2 grams. Now, if you did not want to do it with dimensional analysis, you could do it with percent composition. I already found that my percent composition is 21.2, and it's very simple to find percent composition. So I would just multiply my percent of 21.2 times the total, 402 grams, and I'd get 85.2 grams of nitrogen. That N should be there, you need your unit. Both of these are the exact same answer. You can solve them whichever way you feel more comfortable with. So for empirical and molecular formula, there are 2 formulas that we're going to be asked for throughout AP, and those are the empirical and the molecular formula. These are related to each other, and sometimes the problems will ask for one, the other, or both. Since a formula such as ammonium sulfate relates to the number of moles of each element present, the molecular and empirical formulas deal with the moles of each element in the compound. So my example for an empirical formula, CH2O. Because this is the lowest whole number ratio of atoms, I can't simplify this anymore. Generally, we use this to determine a ratio of elements. There's a 1 to 2 to 1 ratio here. And this can be used to determine the molecular formula. And in this class, what we'll be using this with is percent composition, what we just looked at, and for combustion analysis, which is where we'll start tomorrow. For molecular formula, it shows the actual ratio of atoms in a formula. It's usually found from the empirical formula. So if we find the grams in the compound, we can use this to determine the moles of that compound. And in lab, we will use molecular formulas in 3 ways: for colligative properties, titration, and gas laws. So my step to finding an empirical formula is given grams, we're going to start at step 3. But if I'm not given grams, if I'm given percents, I'm going to start at step 1. So if you're given a percent that I have 28.2% nitrogen, well, I'll just assume I have 100 grams, which gives me a starting number of grams, right? If I assume I have 100 grams, then 28.2% would be 28.2 grams. You can just convert the percent into grams. Then starting with grams, we convert grams to moles, divide by the smallest number because we're trying to find a ratio. If we end up with a decimal place, such as 0.5, then look at the fraction. That'd be over 2, so multiply everything by that denominator. We're multiplying to a whole. Now if I'm trying to find the molecular formula, then I have to be given the molecular formula's molar mass, and then I can use the empirical formula's molar mass. So if I say that the empirical formula's molar mass is 12, and the molecular formula's molar mass is 24, then it's very simple to just double the empirical formula. It has twice the mass, so it has double of everything. If the molecular formula had a mass of 48, then it would be 4 times the empirical formula because it is 4 times the mass. The ratio must still be the same. So we just multiply by the difference in mass. We can also find it using laboratory data, and we will do that later on in the year. But I'm going to be focusing on molecular and empirical and their relationship for now. And tomorrow, this is where we will start, is going through an example problem. Flip to the second to last page in this packet. Your homework tonight will be to do numbers 23 through 27. Don't worry about 21, 22, or 28 yet. We'll start there tomorrow. But you need to do numbers 23 through 27 on a separate sheet of paper to turn in tomorrow.